Block 1. The Unsettling Truth, Gravity versus Quantum Mechanics. Hello everyone, and welcome back to the channel. Today, we're venturing into the deepest, most perplexing chasm in all of modern science. It's a place where our two greatest theories about the universe, the very pillars upon which our understanding of reality is built, collide and break down. This is the story of a fundamental conflict, a paradox so profound it's often called Einstein's worst nightmare. This is the battle between general relativity and quantum mechanics. On one side of the ring, we have the reigning champion of the macrocosm, Albert Einstein's theory of general relativity. Published in 1915, it is a theory of breathtaking elegance and power. It completely redefined our understanding of gravity. Newton saw gravity as a mysterious force pulling objects toward each other. Einstein revealed it's not a force at all, but a consequence of the geometry of the universe itself. Imagine a stretched-out rubber sheet. This is spacetime. Now, place a heavy bowling ball in the center. The sheet curves and dips. That curvature is what we perceive as gravity. A smaller marble rolling nearby doesn't get pulled by the bowling ball. It simply follows the curve in the sheet created by the ball's mass. This is how planets orbit stars and how galaxies hold together. General relativity has been tested to incredible precision. It predicted the bending of starlight around the sun, the subtle wobble in Mercury's orbit, and, a century later, the existence of gravitational waves, ripples in space-time itself, which we finally detected in 2015. It is the undisputed rulebook for the large, the massive, and the cosmic. It's smooth, continuous, and deterministic. Given enough information, you can predict the future of a system with perfect accuracy. Now, let's enter the other side of the ring, the chaotic, bizarre, and mind-bending world of the microcosm. This is the realm of quantum mechanics. If general relativity is an elegant symphony, quantum mechanics is a frenetic, unpredictable jazz solo. This theory describes the universe at its most fundamental level, the behavior of atoms and the particles within them. And the rules here are utterly strange. Particles can be in multiple places at once, a state called superposition. They can be instantaneously linked across vast distances through a phenomenon Einstein called spooky action at a distance, now known as quantum entanglement. And at its heart, quantum mechanics is probabilistic, not deterministic. You can never know with certainty where a particle is or what it's doing. You can only calculate the probability of finding it in a certain state. It's a world built on uncertainty and quantized packets of energy. Reality at this scale isn't a smooth sheet, it's a pixelated, jittery, and chaotic dance. For decades, this division has worked perfectly fine. Physicists use relativity for galaxies and quantum mechanics for atoms. But what happens when these two worlds are forced to meet? What happens in a place that is both incredibly massive and incredibly small? This is where the nightmare begins. The two most obvious places where this collision occurs are at the singularity of a black hole and at the moment of the Big Bang. In these extreme environments, you have an immense amount of mass and energy crushed into a point of near zero size. To describe this, you need both theories. But when you try to combine their equations, the entire structure of physics collapses. The math doesn't just get difficult, it breaks. The equations spit out nonsensical answers, like dividing by zero or calculating probabilities greater than 100%. They produce infinities, which is the universe's mathematical way of screaming, "You're doing it wrong." This isn't just a minor disagreement, it's a fundamental contradiction. One theory describes a smooth, predictable universe, the other a pixelated, probabilistic one. They cannot both be the complete story. This is the central crisis of modern physics and why finding a single, unified theory, a theory of everything, is the holy grail for physicists. It's the quest to write the one true rulebook for reality. Block 2. When rules break, the cosmic catastrophe, and search for unification. So, we have this profound schism running through the heart of physics. But what does it actually mean for reality if gravity, as described by Einstein, truly breaks the rules of the quantum world? This isn't just an abstract problem for mathematicians on a blackboard. The implications are mind-shattering and point to a universe far stranger than we can imagine. Let's explore the cosmic catastrophe that this paradox implies. The most famous battleground is the black hole. According to General Relativity, once something crosses the event horizon, it's destined to be crushed into an infinitely dense singularity, its information lost forever. But a core principle of quantum mechanics, called unitarity, states that information can never be destroyed. It can be scrambled, hidden, or rearranged, but it can't be erased from the universe. This is the famous black hole information paradox. Stephen Hawking added another twist with his discovery of Hawking radiation, a quantum effect that causes black holes to slowly evaporate and disappear over eons. So, what happens to the information of all the stars and planets that fell inside? Does it vanish when the black hole evaporates, violating quantum mechanics? Or does it somehow leak back out, which would seem to violate general relativity? If gravity breaks quantum rules here, it means one of the most fundamental laws of the universe, the conservation of information, is wrong. It would mean that reality has a delete button, and our past and future are not as secure as we think. The problem gets even weirder when we zoom in to the smallest possible scale, the Planck length, which is trillions of times smaller than a proton. At this level, quantum mechanics suggests that space-time itself should no longer be smooth and continuous. Instead, it should dissolve into a chaotic, bubbling mess, often called quantum foam. The very concepts of here and there, before and after, would lose their meaning in a whirlwind of quantum probabilities. If gravity doesn't play by quantum rules, does this foam exist? Or is space-time truly smooth all the way down? If it is, how do we explain the quantized nature of everything else? This isn't just a philosophical question. It's a question about the fundamental texture of reality. The breakdown of space-time at these scales means our entire conception of a stable, ordered universe is just a large-scale illusion. Faced with this cosmic paradox, physicists aren't standing still. They are engaged in a heroic, multi-generational quest to find a theory of quantum gravity, a framework that can finally unite these two titans. Two leading candidates have emerged from this search. The first, and perhaps most famous, is string theory. It proposes a radical idea. At the most fundamental level, all particles, electrons, photons, quarks, are not point-like dots, but unimaginably tiny, one-dimensional vibrating strings of energy. The different ways these strings vibrate produce the different particles we see, much like different vibrations of a guitar string produce different musical notes. In this beautiful symphony, one particular vibration mode gives rise to a particle with the exact properties of the graviton, the hypothetical quantum particle of gravity. In one elegant stroke, string theory could unite all forces and matter. However, it comes with its own baggage. For the math to work, it requires the existence of extra hidden dimensions of space, and it has yet to produce a prediction that we can definitively test with current technology. The other major contender is loop quantum gravity. Instead of starting with particles and forces, it starts with space-time itself. LQG proposes that the fabric of space-time is not a continuous sheet, but is woven from a network of finite, discrete loops. These are the atoms of space-time, the fundamental pixels of reality. In this view, space isn't empty, it's a structure. Loop quantum gravity successfully quantizes gravity without needing extra dimensions, and provides a compelling picture of a universe without singularities. The Big Bang becomes a big bounce. But it too faces immense challenges, particularly in showing how the smooth spacetime of Einstein's theory emerges from these discrete loops at large scales. This grand search, whether through strings, loops, or some other idea we haven't even dreamed of, is the ultimate frontier of science. It's a quest to understand the operating system of the cosmos, to resolve Einstein's nightmare, and to finally read the universe's source code. Do you think we'll ever find a theory of everything? Let us know in the comments. Subscribe for more deep dives, and see you in the next one.